Question number 1.19. A hypothetical engineering stress strain curve shown in figure has three straight lines PQ, QR and RS with the coordinate P00, Q 0.200, R 0.6140 and S 0.8130. Q is the yield point and R is the ultimate stress point and S is the fracture point. Then we need to find out the toughness of the material. Toughness. Toughness is the energy absorbed by unit volume of the material up to failure point, and toughness is equal to the area under stress strain diagram up to failure point. Area under stress strain diagram up to failure point. Here stress strain curve is given, so we need to find out the area of this stress strain diagram. I am dividing this stress strain diagram into three parts. This is a triangle 0.6. This is a rhombus. This is also a rhombus. It should be a straight line. This is a area 1, this is area 2 and area 3. And total toughness is equal to area of region 1 plus area of region 2 plus area of region 3. Now, total toughness is equal to A1 plus A2 plus A3, A1 plus A2 plus A3, A1. A1 is equal to, is a triangle half BH, half into B. B is 0.2, that is percentage strain, up 0.2 by 100 into height. Height is equal to 100. Height is equal to 100. So A1 is equal to 0.1. A1 is equal to 0.1. Then A2. A2 is the shape of rhombus. This is A2, the shape of A2. A2. If the height of this side is A1 and height of this side is B and the width is H, then area is equal to half into A plus B into H. A plus B into H. Here we are converting this shape into an equivalent rectangle. And the height of that rectangle is A plus B by 2. This is the average of A and B. So the A2 is equal to half into A. This side is 100. 100 plus 140. 100 plus 140 into this width 0.6 minus 0.2, that is 0.4. 0.4 by 100. 0.4 by 100. Therefore A2 is equal to 0.48. A2 is equal to 0.48. And similarly A3. A3 is equivalent to a shape of a rhombus. So we can write half into this height 140 plus that height. This height is 130 into width is 0.2 by 100. 0.2 by 100. Therefore A3 is equal to 0.27. A3 is equal to 0.27. Therefore total area is equal to area 1 0.1 plus area of 2 0.48 plus area 3 0.27. 0.27 we get 0.85. 0.85 is the answer. 0.85, that is the answer. Here we need to find the toughness. Toughness is the area under stress strain diagram up to failure point. Therefore answer is 0.85. Then question number 1.20. A square plate of dimension L into L is subjected to a uniform pressure load P is equal to 250 megapascal on its edges as shown in figure. Assume plane stress condition. Young's modulus is given. Young's modulus E is equal to 200 gigapascal, which is equal to 200 into 10 raised to 3 megapascal. The deformed shape is also a square of dimension L minus 2 delta, where L is equal to 2 meter, length is equal to 2 meter is equal to 2000 mm and Poisson's ratio and delta, deflection delta is equal to 0.001 meter, 1 meter, therefore 1 mm, and the Poisson's ratio of the plate is, we need to find out the Poisson's ratio. I am considering a bar and applying a load P, I am applying a stress sigma. Due to this stress, the length of bar increases, at the same time the diameter decreases. In this case, lateral strain by longitudinal strain is known as Poisson's ratio. But in this case, there is stresses are acting in y direction also. In this case, we cannot directly write the direct change in diameter or lateral strain by longitudinal strain. In this case, the lateral strain by longitudinal strain is not Poisson's ratio. Here this is a question given. Here we have to use strain along x direction is equal to stress along x direction by Young's modulus minus mu into Poisson's ratio, stress along y direction by Young's modulus. Then strain along x direction is equal to change in dimension along x direction by original dimension along x direction. Here changing length along x direction. This length L is initial length. This is the final length. Initial length minus final length. We get delta plus delta. This gap is delta. This gap is also delta. So this is 2 delta. And this compression, there is minus 2 delta. This is the gap. This gap is the delta by total length. Total length is original length. Original length is L. So we can write, instead of strain along x direction, we can write 2 into delta by length. Actual length is, I think, length is 2000 mm. 2000 is equal to sigma s, that is P, and the magnitude is P is equal to 250 megapascal, which is compressive, minus 250 by Young's modulus. Young's modulus is equal to 200 into 10 raised to 3. 200 into 10 raised to 3 minus mu into sigma y also minus P, minus 250 by Young's modulus 200 into 10 raised to 3. 200 into 10 raised to 3. Solving this equation, we get Poisson's ratio mu is equal to 0.2. Poisson's ratio mu is equal to 0.2.